In this video, go over complexity analysis and what complexity analysis is and why is it useful, the different types and measuring metrics used to analyze complexity, and finally, how to analyze complexity of an algorithm with a few examples. A coding problem may have multiple solutions or different algorithms that could be used to solve that problem. We use complexity analysis to evaluate the performance of an algorithm. This helps us find the best possible solution. So, we analyze the complexity of an algorithm to evaluate its performance. That way, we're able to find the best solution which has the most efficient performance to solve that coding problem. When analyzing complexity, we look at the program's time and space complexity. Time complexity is the amount of time the program takes to run. Space complexity is the amount of memory the program takes. There are three metrics that are used to measure time and space complexity: big O, big omega, and big theta. In this video, we'll focus on big O, which is the most relevant, although it is very important to understand the other two metrics. But big O analyzes the algorithm the worst case. What that means is, for example, if we have a list of integers that are unsorted and we want to write an algorithm that would find the index of a target integer in this list. So let's say our program goes through each integer until it finds the target. Now, the target could be in the first index, which would be the best case here, since it only took us one step to find the index of the target. Or it could be in the middle of the list, which could be the average case. In the worst case, the target is at the end of the list. Since we have to go through each of the integers to get to that last index, this is the worst case as it takes the most time to run. And big O evaluates programs based on their worst case. It is important to know the input size and the number of operations when calculating big O and analyzing an algorithm. In this graph, we have big O values that are used to measure time and space complexity. As you can see, in the x-axis we have the input size, and in the y-axis we have time. Big O of 1, which is constant time, is the fastest as it does not depend on the input size. And then we have logarithmic time, linear time, and other big O values as well. These big O values are used to measure the time and space complexity, and they're ranked in the following order, from fastest, constant, until the slowest, or the ones that take the most time to run, which is factorial or exponential. So here are a few examples when evaluating big O. In this program, we're adding two integers, 7 and 3, and storing their sum in x. This takes big O of 1 as it runs at a constant time. It runs at a constant time since it does not depend on the input size. So if the input size increases, this will not change how fast this program runs. Here we have an example of a for loop which runs until I is less than n. So as the input size increases, this will keep running and will take more time as the input size gets bigger. And in this third case, we have quadratic. It is usually represented through nested loops. So the way we evaluate this is by looking at the outer loop first, which takes O of n, big O of n to run, since it will keep running until I is less than n. Then we have another for loop, which also has a time complexity of O of n. And finally, this print statement here in C++ is running at a constant time, since it does not depend on the input size n. So the way we calculate big O of this program is by multiplying all the big O's together and finding the product, since they're all nested here together. So the product of this would be O of n squared. And in the worst case, we're gonna keep looping up until n in this outer loop, and keep also iterating inside here until n, which will keep printing this with the big O of n squared. We have two main rules for big O. We drop the constants, meaning that if we have 2 by O of n, we could just say that the big O of this algorithm is O of n. Or if we have 3 by O of 1, this is just O of 1. We use this as theoretically, but in reality it is important to consider the constants, since if we're multiplying by very large numbers, then that would affect the performance of an algorithm. But for when learning about this theoretically, we just care about the main big O, and we drop the constants. Another thing is the degree. So if we say we have multiple big O's, for example, O of n squared plus O of log n plus O of 1, the big O for this algorithm would just be O of n squared, since we look at the big O with the highest power. Let's look at a few examples. So in this case here, in this line, we are adding two integers together and storing them in y. This runs at a constant time, or big O of 1. Then we have a for loop that runs until a constant time and executes this print statement at a constant time as well. So we have O of 1 and O of 1. So not always a for loop would have a linear time. If it's running up until a constant time, then the big O of the for loop is also constant, since it is not affected by the input size. And the big O of this program would be O of 1 plus O of 1 by O of 1. What is just O of 1? In this other example, we have a set of conditions. When x is greater than 0, then we have a program that runs at O of 1, big O of 1. And if we have x is less than 0, then we have a program that runs at a O of log of n. Else, the code with big O of n squared runs. In this case, the big O is O of n squared, since although x might be less than 0 and this code executes, we always want to consider the worst case when dealing with big O. And finally, for the space complexity, we also use big O. But when measuring space complexity, it's, for example, if we're initializing and initializing an array of size n, then this would be O of n. And if we had a nested array, then that would be O of n squared and quadratic. If our program does not store any elements, use data structures, then it is not using up any memory, so it would just have a constant space complexity. And that would have the least, or occupy the least amount of memory.